Okay, here we are looking at resonance structures. You may not hear this from other people, but let's just be honest about it. Resonance structures occur when Lewis structures just don't really work for what's going on with the molecule. Lewis structures tend to work fine for a lot of molecules, but we're going to find there are times when the Lewis idea of what the bonding in the molecule looks like isn't right. It's just not right. So let's look at these situations. And when Lewis gets it wrong, we put in resonance structures to kind of say, oh, okay, here's what's going on. Let's start with NO2-. If we do the Lewis structure for NO2-, we find we've got 18 electrons. You generate this guy right here, and we realize, okay, nitrogen does not have its octet, so we're going to form a double bond, take one of the lone pairs, make a double bond here, and we get this beast right here. Oxygen double bond to this nitrogen with its lone pair, single bond this oxygen. It follows all of our nice rules for Lewis structures. This nitrogen has its octet, the oxygens have their octet. We've got a -1 formal charge on this oxygen. The formal charges add up to the overall formal charge. The formal charge is on the more electronegative atom. And so that looks nice. The problem is when we look at NO2-, when we look at this Lewis structure, we see we have a nitrogen-oxygen double bond and a nitrogen-oxygen single bond. And we remember from previous video that double bonds are shorter than single bonds. So we'd expect one shorter nitrogen-oxygen bond, one longer nitrogen-oxygen bond. The problem is when you actually look at this ion, you find that both nitrogen-oxygen bonds are the exact same length. You don't have one shorter than the other. Even more, the length of this nitrogen-oxygen bond in this molecule is shorter than what you would expect if it were a single bond, but longer than what you would expect if it were a double bond. So the nitrogen-oxygen bonds in this molecule are both the same length, but they are in between single bond and double bond length. Well, that's not what this says. This molecule here says we've got a short bond and a long bond. Reality, they're both the same length and they're halfway in between short and long. So, how do we make this structure that we've come up with, it looks nice, how do we let everyone know that it's not quite right? What we do is we say, okay, this is one resonance form of NO2-. We chose this oxygen over here to create the double bond. Couldn't we have chosen this oxygen over here and used a lone pair here to do it? We could have. So let's draw the structure if we had this oxygen over here making the double bond, and that means the double bond would be on the right side. Okay. To indicate that these are resonance forms, we have to draw this arrow in between them that looks like this. All right, when you're indicating resonance forms, make sure you draw that very arrow right there. If you were to draw this, that would be wrong. So do not draw that. This is equilibrium. That's not resonance, that's equilibrium. If you were to draw this arrow, kind of two lines in the middle, that is wrong. I have no idea what that means in chemistry, but it's definitely not resonance. Do not draw those arrows. You draw this single arrow with arrow points at both ends. That means resonance, and that's all that arrow means in chemistry is resonance forms. Okay, so what does it mean when you draw these resonance forms? What it means is, when you see this, when you see I've got this structure, resonance form, this structure, I've got these two resonance forms, what that is telling you is this is not right, this is not right. The real answer is some combination of these two. You can say, okay, here this is a double bond, here it's a single bond. Neither one of these is right. The answer is somewhere in between that. Here's a single bond. Here on the right side is a single bond. Here on the right side is a double bond. So a single bond is not right. A double bond is not right. The real beast is somewhere in between. That's what resonance forms tell us. And so you're probably asking, well, then why can't you actually draw the real thing? Well, let's show you. The real thing is called the resonance hybrid. All right. The real thing is a combination of those two, and we're going to tend to draw the resonance hybrid like this. Okay, this isn't a, if we look on the left side of the nitrogen, double bond is not right, single bond is not right, so we're going to draw it here as kind of like a bond and a half-ish. We're going to draw a solid line to represent, there's definitely at least a single bond there, and then a dotted bond to represent, it's not quite a double bond, but it's more than a single bond. And we'll draw the same for the other side. The problem exists is, you note in this resonance hybrid, I did not draw the electrons because, well, where do the electrons go? Is this a double bond or a single bond? How many electrons are in that dotted line there? Is that one electron? Ooh, that's getting kind of nasty, because if that was one electron in the bond, in this bond, that means then how many electrons this oxygen has to have its octet. And so if we drew the other electrons around this oxygen, okay, 1, 2, 3, 4, 5, 6, 7, we would have to like put a lone electron by itself on that oxygen. Or if you look at the molecule, there is no lone electron on that oxygen. Yeah. Does this sound confusing? Yeah, that's the whole problem here. This isn't right, so you draw this resonance hybrid, and it still has its issues too, because when you draw the resonance hybrid, you're going to have a heck of a time drawing where the electrons are. Oof. So you can see that Lewis structures have broken down. We can't really use the Lewis structures very well to show you what's going on. You just have to do it this way. We say, okay, we're going to draw resonance forms. This isn't right because we could have taken a lone pair from the other oxygen. That's not right either, because the truth is both bonds are the same length, somewhere in between double and single bond length. We cannot actually draw the resonance hybrid while taking into account all of the electron lone pairs on the atoms. We just have to, in our brain, know kind of what's going on. You're probably thinking, man, isn't there a better theory, a better way of doing this that will tell us exactly what's going on? Good news, there is. We're going to talk about it at the end of the next chapter. It's called molecular orbital theory. Bad news, molecular orbital theory is extremely more complicated than Lewis structures. So complicated, in fact, that's why we just go with resonance forms, because we're like, okay, we're going to say that the resonance hybrid is a combination, and we're going to know that when we draw these two things, and we're going to imagine what the reality is, because if we actually did the molecular orbital theory, it would take us 5 days to calculate what's going on versus 2 minutes. So, yeah, molecular orbital theory, we'll get to it. It gets pretty nasty pretty quick. So there is a better theory out there, but for now we're going to stick with resonance forms. So let's do an example of this. NO3 minus. If we add our electrons, we find there are 24 electrons for NO3 minus. Nitrogen's in the middle, 3 oxygens on the outside. Let's put in those 24 electrons. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Boom. 24 electrons in there. Does nitrogen have its octet? No, it does not. So I'm going to take 2 electrons here and give nitrogen its octet by forming a double bond. I'm going to draw this guy up here. O, single bond N, double bond O up top, single bond over here. Add all the electrons, 1, 2, 3, 4, 5, 6 electrons around this atom. 2 lone pairs on the top oxygen. 1, 2, 3, 4, 5, 6 here. If you add up your formal charges, you will have a negative formal charge on this oxygen, negative formal charge on this oxygen right there. Let's see, and ooh, you'll find a positive formal charge on this nitrogen. Note, negative, positive, and negative add up to -1, our total charge of that ion, so that works. And the way you know that we're going to need resonance forms here is when you say, okay, I chose to make a double bond using this top oxygen. Couldn't I have used this other oxygen and made the double bond over here and left these two as single? Why, yes, I could. Well, couldn't I have done a double bond here? I could have. What makes this top oxygen so special that it got the double bond and these two get the single bond? The answer is nothing makes it special. Therefore, we realize we need resonance forms. Anytime you're saying, oh, well, which oxygen or which terminal atom do I choose to make the double bond with? And your answer is, well, you could have chosen a number of them. Then you know you need resonance structures. So we've got this guy here. It's resonance structure. Make sure you draw the resonance structure. We are going to, let's move the double bond to the right oxygen, put in all the electrons. Minus. And then we have to have, ooh, there's another resonance form where the oxygen on the left has the double bond. So these are all the resonance forms, all three resonance forms for the nitrate anion. So question, what does nitrate really look like? Question, how many double bonds does the real nitrate anion have? The answer is 0. Question, how many nitrogen-oxygen single bonds does nitrate really have? The answer is 0. The real resonance hybrid, what nitrate really looks like, is a nitrogen with 3 oxygens around it. All 3 nitrogen-oxygen bonds are the exact same length. They are shorter than you would expect a nitrogen-oxygen single bond to be, and they are longer than a nitrogen-oxygen double bond should be. And that's what nitrate really looks like all of the time. Extremely important here. It is not, repeat, not the case that nitrate sometimes looks like this and sometimes this and sometimes this. The double bond is not alternating in between the oxygens. 100% of the time, none of these structures is right. 100% of the time, the real beast is a nitrogen with 3 oxygens around it, and the bonds are a little bit shorter than single bonds and a little bit longer than double bonds. 100% of the time, nitrate looks like this. It never looks like any of these. All 3 of these are wrong. The double bond is not alternating between the oxygens real quickly or anything like that. All these are wrong. This is right. But then this has got all sorts of troubles, because if you actually try to add up how many electrons around here, you've got like 4 1/3 electrons on this oxygen. It's crazy. And it's a problem with Lewis structures. Now, Lewis structures deal with electrons as particles, as that electron beast. If you look at it as electron density, the probability of finding an electron, all we're saying is the probability of finding the electrons here is larger than the probability you expect to find electrons if it was a single bond. It's a lower probability than you'd expect to find electrons there if it was a double bond. That's all we're really saying. Note the other thing when you're doing resonance structures, you can only move electrons. You cannot move atoms around. So you can't put an oxygen and put it over here or something. Another way of saying that is you cannot break any single bonds. When you draw the skeletal structure, this nitrogen has to have at least 1 single bond to this oxygen, at least a single bond to this, and at least a single bond to that. And then the only thing you can move around to make your resonance forms is electrons. You cannot move atoms.